Hi everyone, my name is Alyssa Fossen, and for my summer program research, I looked at particle size distribution and chemical composition of aerosols in coastal Peru. So let's start off with why. Why do we care? Well, for the public health. So everybody is constantly breathing in particles and aerosols. Most of those larger particles get caught in bodily defense mechanisms such as nose hairs. However, once particles get smaller, they're able to more easily bypass those mechanisms and get within the lungs and then to the bloodstream, which obviously can cause health issues. So knowing the chemical composition of these smaller particles, about 10 microns in size and under, excuse me, which is what we're specifically looking at, we can know what people are breathing in and hopefully where it's coming from so that it's able to be prevented or changed and hopefully stop some air pollution or prevent some health issues. Another reason was also climate change. So clouds are formed from aerosols, and white fluffy clouds actually reflect light, so it cools the area beneath them, whereas heavy, dense black clouds absorb heat and traps heat in, almost like a lid on a jar. So it's a natural heating and cooling system. And so somewhere that has a lot of smog then gets very heated and traps in heat. So it is important to know what particles you are dealing with. But why specifically Peru? Well, Peru and Chile have a lot of fog, so there was a lot of data, and it's a good location to look at all of this. And also, this research that I did has been done numerous times worldwide. However, in South America, it's been far and few between, so I just wanted to do something to stand out. So our sampling location was in Catarindo, Peru, and that was about 1 kilometer from the city Malindo and about 1 kilometer from the ocean. And here is our approximate location of where we sampled. The star right here is actually a copper smelter, which we will talk about a little bit towards the end. And then also blowing the image up, you can see here is about our approximate location, again, of our sampling. And this is our aerosol samplers. We use a 4-stage impactor, which can be seen here on the right. Essentially, it's a metal kind of grate vent that sandwiches in filters that are finely woven strands of glass or quartz. I'm not entirely sure which one we used. And each one is gets smaller and smaller so it can catch different particle sizes. So the top filter is going to catch the biggest ones. The smaller particles kind of get pulled through and get caught into the next one, or else get pulled through until they fall onto the backup filter, which is going to catch everything that gets left behind. As you can see here, our stage 1 is the biggest and stage 4 is the smallest. However, our stages were reversed. So stage 4 went up to about 10 microns, stage 1 went down to 0.95. However, our backup filter, or stage 0, caught everything else. So how do we collect this data? We were specifically wanting to look at our anions of chloride, sulfate, and nitrate. And to do that, we took each filter, we put it in a plastic bag with 15 mils of water, let it sit to get all the particles and anions off the filter. And then as you can see here in the image, we poured them into a vacuum filtration system. And then taking the liquid from that, we're able to put it into an ion chromatography machine. And the IC machine then gave us data such as pictured on the bottom, the different peaks of our anions. We do have phosphate on here, but we found we didn't really have much in our samples, so we kind of threw that out. And then using a bunch of math, we were able to integrate the area under these peaks and use it for our data analysis, such as for chloride. And here we have our data looking all pretty. We're able to see that there is a significant amount more of particles in our stages 3 and 4, which were our largest stages. And there is a large amount of variability, but why is our chloride in these larger stages? And this was presuming that our chloride came from sea salt. And the mechanism for turning sea salt into aerosols creates large particles. So here on the left, we can see that fog that I was talking about. This is mist coming in from the ocean over the coast. And then on the right, we have the mechanism for our particles. So bubbles from the water come up and pop, or wind agitates the water, and again, particles form. However, it may happen, and droplets go into the air. The water evaporates, leaving us with our aerosol particle. And smaller particles don't really survive this process, which is why we see a large amount of large chloride particles. And this is also consistent with all of the other studies that we looked at. And here on the left, we can see the makeup of our seawater. The top is the Northern Pacific Ocean, so it's not as important. The bottom, however, is the Southern Pacific, which is where we were at. And as you can see, there is not a whole lot of organics or vanadium or anything else, but there is a lot of sea salt. And as the diameter increases, there is a lot more of these particles, which is consistent with our results. However, cut off right about 2 microns in the study that this is from, and ours started at 3, however, it is still applicable. And then here on the right, we have, again, the makeup of our seawater with the concentrations. These are the most present ions, chloride having the most, which were then later used for our sulfate ratios, which we will see in just a few slides. As for our nitrate, results were a little less clear. However, there is the most still found in stages 2 and 3, so our middle stages. And we didn't have a lot of data to work with for our nitrate. There was not as much of the sample present, so it was a little trickier to work with. However, we were able to conclude that due to the nature of nitrate, where the gas is highly reactive and it bumps against the surface, which forms an aerosol, that it needs to have a large amount of surface area to react. And so our 2 graphs here, the one on top looks at our square, so our surface area, and the bottom one looks at our cubed, so our volume. You can see that our square has a peak right in the middle, and our cubed has peaks later on in the graph. And this is because of math, where if we have a 0.1 diameter particle, if you square it to get the surface area, you'll have 0.01. However, if you cube it to get the volume, you'll have 0.001. So there is a lot more in those middle ranges, whereas something at 10 microns in size, you square it, you get 100, you cube it, and you get 1,000. And that is why we have our nitrate mostly in those middle stages, because it's ideal for the reaction. And for our final anion, we have sulfate. And this one is thankfully very clear as well, where we have almost all of it residing in our backup stage, so our stage 0, where it catches all those little particles. So why in the backup? Well, we figured that most of our sulfate is actually non-sea salt sulfate. Pretty self-explanatory. It's simply sulfate that does not come from sea salt. And so we took our amount of non-sea salt sulfate, or our expected amount of non-sea salt sulfate, and divided that by our total amount of sulfate, expecting to get around 1, which would be ideal. However, only stage 0 had something close to that, and as the stages increased, as you can see, I plotted them that way, the ratio got even smaller. So where does this non-sea salt sulfate come from? We presume either dimethyl sulfate or from a copper smelter. DMS comes from phytoplankton, which is measured by chlorophyll. So we have a NASA image here, and you can see that there are high amounts of phytoplankton, or DMS. And then our copper smelter is, as I mentioned before, there's that smelter close by, and in this process, it releases SO2, which turns into sulfate and gets into the atmosphere. And so in conclusion, our chloride comes from sea salt, our nitrate is due to an increased surface area, and then our sulfate comes from either DMS or a smelter. And for future work, we want to look at sodium, which can give us more consistent ratios and data, and to look at cation analysis, again, to get more exact information and knowing more about the makeup of these particles. So for acknowledgements, here pictured is the RAU program that I was part of. They're all amazing. And here are my references. Thanks for joining me today.